Wow, I did. I got distracted right while I was going to pick the board.
And another thing.
If you recall, we talked about the curl of the vector field, which is the tendency of the vector field to swirl around or curl. It's the swirliness of the vector field. And it's this cross product of the del operator and the vector field. So at each point, we're calculating how much the vector field is turning around, how much the vector field is going around the point. It makes sense that if we got this curl, it's based on the cross product. The cross product is subject to the right-hand rule. So if it's swirling one way, we'll have positive curl. If it's swirling the other way, you'll have negative curl. One of these days, I'll come up with a more elegant way of demonstrating that than just sticking my hand in front of the camera going, hey, but it's not today. I'm hoping that I could just like ride that one out until the end of my career and then not have to worry about it, but we'll find out. Someone's going to come along with some slick animation. I'm going to be the old man yelling at a cloud. Back in my day, we just had to stick our hand in front of the camera. So yesterday we did a calculation of the curl, and it was with this generic vector field, so we could practice making the calculation. And we looked at the curl vector, and we're like, oh, okay, that's the curl. What does that mean? It's like, well, it's how swirly the vector field is. And everybody in the room was like, oh, dude, not helpful, because we can't picture that vector field. So what I want to do today is grab a vector field that we can picture, that we can see swirling around. And so let's grab a vector field, minus y I hat plus x j hat, and let's just keep things flat in the z. I want it swirling around. I'm just going to pick a vector field that is just swirling around. So if you would recall, this is a vector field that has concentric, whose flow lines are concentric circles centered at the origin. So if we just kind of follow the flow lines, if we just kind of follow the flow lines, we're just kind of like cruising around like this. We're going to expect that the curl should be pointed up, because we can see that this is like these swirls are nice and flat in the XY plane, and perpendicular to that, where our thumb is going to be going, should be coming straight out the page. Let's calculate. So F1 is just minus y, F2 is x, and F3 is 0. So our curl of F our I component is F3 with respect to y minus F2 with respect to z. Because remember, our I component is going to not have anything to do with F1, because that's in the same column as the I. So the I with dx with the F1, that's not going to be in the I component of our cross product. So F3, the partial with respect to y of F3 is 0, minus the partial of F2 with respect to z is also 0. This always looks so concerned, but we shouldn't be concerned. This is exactly what we expected. We expected the curl to be coming straight out the page, have no x and y, be all k, or no I and j, all k. Minus our j component is going to have F3 and F1, because F2 is in the j column. And we're going to use partial x and partial z, because partial y is in the j column. So we do 3 with respect to x, 0, minus 1 with respect to z, 0. Once again, the expression looks so concerned, but 0 is what we were expecting. Let's see what happens in k. Now, we should expect some positive values for k. Let's find out. So the k is not going to involve f3 or partial z because that's all in the k column. And this is a cross product, and we crossed out that k column. So we're going to do 2 with respect to x minus f1 with respect to y. And this is what we expected. No I plus no j and some positive k. So our curl is coming straight out the page. And it looks to be constant. We shouldn't be surprised by the nice constant value of k because the swirliness seems to be nice and uniform swirliness everywhere. So that's giving us some information. We have nice uniform swirliness. We just got stuff going around a record player. The record player is going backwards for some reason. I don't know. Messages in some Beatles albums. I don't know why it's going this way. Wait, records do go clockwise, right? Do they usually go clockwise or do they go counterclockwise? There's a room full of people that haven't seen a record player for a long, long time. I have it in my house. I even have a bunch of records, but I mean, Spotify. Counterclockwise? All right. Sorry. That's okay. No, clockwise. So, this is as expected. The swirliness is going counterclockwise, and if we go counterclockwise with the right-hand rule and a cross product, it's going to go up, and that's what's happening. Furthermore, if I multiply by -1, and do positive yi minus xj minus 0k, which is the same, then the curl of f, just by properties of cross products, is going to be -1 times the curl of negative f. Yeah, I don't know if this is a more coffee problem or a less coffee problem. I just know which solution I'm going to be applying. So the curl of negative f will be 0i and 0j, but minus 2k. As our partial with respect to x will be -1, and our partial with respect to y will be +1. So -1 minus 1 will give us a negative. And so if we swirl around the other direction, once again, with this nice uniform swirling, now we're curling around this way, and our curl is going down into the page. So if we think about the fundamental theorem of calculus in Stokes' theorem, where we want to calculate the curl of a vector field, at all the points on some surface, we can calculate this by looking at the vector field itself around the boundary of the surface. Remember that the boundary of the surface, C, the curve C, is oriented such that the surface is on the left as we travel around the boundary. That is, C is counterclockwise. So we've got C keeping the surface on our left. It's not round, but we can see it's going what we would describe as counterclockwise is our positive direction. That's our boundary C. What we're calculating at all the points on the surface is how swirly the vector field is. So at each point, each little piece of area, we're calculating how much it's swirling around, and then how much it's swirling around, and then how much it's swirling around. And we're just adding up all this swirliness at all these points. And in fundamental theorem of calculus fashion, we can when we add up all the swirliness of the curl, we can just add up the vector field around the boundary of the surface. When we integrate a derivative over a set, we evaluate the function at the boundary of the set. I don't know why I had to redraw that one. It's bothering me. And so that's how Stokes' theorem fits into the concept of the fundamental theorem of calculus, where we integrate a derivative over a set by evaluating the function at the boundary of the set. And this is what the derivative represents in this context. It represents how swirly the vector field is. Any questions? So note that we've talked about the ideas of our fundamental theorems of calculus. We haven't got into any of the calculations of the fundamental theorem of calculus. That's because we got to spend a week just thinking about it before we start letting calculations get in the way. Because one of the things we're going to have to do is parameterize a surface. Just like back when we were doing line integrals, we had to parameterize the curve. Now we've got to parameterize a whole surface just to make a calculation. Any questions? Comment? Snide remark? Clearly that was very distracting. Yeah. Yeah. Yeah, it's crazy how everything works out so well, how everything lines up so much. It's also funny that we discover the physics stuff first, and then the math comes along, and the math's like, oh, check it out. And then the math acts all high and mighty, and says, well, of course. Because for a long time, the math is like, well, I don't know, seems right. And then something comes along and says, oh, we just confirmed this. The math says, yes, of course you do. Of course. We're just waiting for you to catch up. This is why I went with math, because when I was in engineering and physics, all the labs had to work out. I go, let's just do some calculations. And my friends were like, oh, dude, your version of Mythbusters is gonna suck. So, does everybody know what Mythbusters is? I reference record players, so I'm gonna have to update that a little bit. Let's move forward a little bit. Everybody knows Mythbusters, right? Most Mythbusters episodes are a math problem. But no one wants to watch a math problem. You know what I mean? Like, you know, like the one where they did the inverted boat, and they had the inverted boat, and they're like, oh, Johnny Depp and Orlando Bloom, you can't do that. That's not how it works. Because the weight that you need to pull the boat down is how much does the water weigh if you fill the boat up, right? Yeah, they had to fill the boat up so they could bring under, and then they just had like people with scuba gear and pirate gear below the waist, but scuba gear above the waist, like walking with a boat. But that thing had to be full of water, unless Orlando Bloom and Johnny Depp weigh like 3,000 pounds total. It's like, no. Right, the heavy boots. It's just like, not how that, you know. It's a math problem. But no one wants to watch some nerd do some calculations. Right. They want to watch some different kinds of nerds build something that explodes. That's good television. That's why that Mythbusters episode you get for free on the television. Well, minus what you have to pay to watch it. And then and this class you have to pay for. Because my nerd demonstrations are way less impressive than Mythbusters. I don't know. I think we have the big red buttons for things that start when things start exploding on campus. All right. That's going to do it for today. That's going to do it for this week. I want you to think about the fundamental theorems of calculus, the structure of the fundamental theorem of calculus. Think about divergence and curl, and think about how that fits in with your fundamental theorems of calculus. That's going to do it for today. That's going to do it for this week. I will see you all on Monday. Everybody have a good weekend, and thanks for playing.